Hi guys. Wow, I bet you wish you were here today because wow, we're doing reducible second order differential equations. My goodness, you know what? We haven't had second order differential equations in this chapter, and yet we're sneaking it in. By the way, this is not in our textbook. This is something that naturally fits in to this chapter, though. Different textbooks do include something like this because, believe it or not, what we're going to do is change a second order differential equation into a first order one by a substitution. So here's what's going on at the heart of it. Let's just say there are two cases here. I want to do this quick. Let's say case one, y is missing, but we do have a differential equation involving y prime and y double prime. But y itself is missing. How about wherever we see y prime, wherever we have dy dx, we actually say, you know what, let's just call that p. And then if we took our second derivative of y, you might think about that. That, of course, would be p prime. So what's the advantage of this? Well, you can see incredibly fast something wonderful is going to happen. You're going to have a first order differential equation. Once you make that substitution, we're going to expect to find two arbitrary constants. So let's take a look at example 1. We've got x y double prime plus 2y prime equals 6x. We can say, wow, this is great. There's no y. So let's let p equal y prime. And then guess what we're going to let equal y double prime? We're going to let p prime equal y double prime. So let's rewrite it. Look familiar? All of a sudden, kids are probably saying, hey, that looks just like a linear differential equation that we've been dealing with all chapter long. You bet. So what do? Well, real quickly, we could say let's divide everything by x. And we have p prime plus 2 over x. P is equal to 6. Hey, we have a test coming up in the near future. Great time to review here. This is perfect preparation for that. How would we solve a linear differential equation like this? Integrating factor, right? We'd say e to the integral of 2 over x. Whatever is out in front of our dependent variable here, that's going to lead us to our integrating factor. You can pull out a 2, and of course the integral of 1 over x, we could say, is just a natural log of x. This becomes e to the natural log of x squared. Guess what that becomes? X squared. So tell you what, multiply everything by x squared. Every little piece of the puzzle here gets multiplied by that. And we have x squared p prime plus, well, technically this just becomes 2xp equals 6x squared. All right. This left-hand side we can think of as what? A product rule. What times what? X squared times p. And you can see this is exactly what's taking shape by the product rule. X squared times the derivative of p plus the derivative of x squared times p itself. That fits perfectly. Now what do we do to both sides? Integrate. Don't be bashful. Okay. So we got x squared p is equal to, hey, what's the antiderivative here? 2x cubed, right? See how much fun we're having here? I told you guys you wish you'd be here. Okay. So look at all this. This is great. You know, sometimes kids are looking at this, they're like, hooray, we're done. Not quite. Not quite. First of all, we could divide by x squared, and that would be fine. You know, we could definitely, make this look a little bit nicer. This becomes 2x plus, here's c1 times x to the negative 2. But this is not something that even showed up in the original problem. P was just temporarily filling in for what? Y prime. Wow. Or if you'd rather, dy dx. I mean, they're the same thing, aren't they? So let's take another antiderivative, guys, and what do we get? X squared. Ooh, bump up our power to the one step higher, that's -1. But divide by that, so we get negative C1 all over x, that's x to the -1, plus, here's a second constant. Hey, look at that. We are done. So you just make a couple of changes here, and a problem that would seem to be very much more complicated than what we've been doing earlier becomes quite doable. Okay, we doing okay? Second half, case 2. We're making some great big assumptions here, but it's good. We said before, what if y was missing? Well, now we have to address this other scenario. We're going to say, well, now case 2, what if x is missing? So you've got a y double prime, you've got y prime. You could have other forms of y in this differential equation, but x must be gone. Well, where are we going with this? Same beginning, same exact beginning. You can say, let's say wherever we've got y prime, which is dy dx, call that p. But you see, the problem is, if there's no x in this differential equation, we don't want to see any x show up whatsoever. In other words, we'd like to think about our second derivative only with respect to p and only with respect to y. We don't want x to have a place in this. So how on earth do we deal with this? The answer is with the chain rule. With the chain rule. Here's how. Y double prime, guys. You could say, well, isn't that dp dx? Indeed it is. That's what we did before. But hopefully you remember the chain rule. dp dx could have this connection right here. This is actually a Leibniz form of the chain rule, writing it out with differentials. We're saying, what if there's a function y that p is defined as a part of, p is a function of y, but ultimately y is a function of x. That's what we're saying. Take your derivative of p with respect to y, but then multiply by dy dx. But what did we call dy dx? Look at our first substitution. We called it p. So what you're really getting at is right here, where you see dy dx. Instead of writing dy dx, replace that with p. So y double prime, according to the chain rule, is dp dy times p. We could just move that p out in front. So that is how we make this adjustment. We're going to solve for p and then substitute and move on from there. So let's immediately jump into example 2 and try to finish it up. We're going to say, okay, let's let y prime equal p, just like we did right here. We could say wherever we see a y double prime, we're going to say that's p times dp dy. Okay, that's what this statement right here is ultimately getting at. And like I said, this all is proven via the chain rule. So what are we getting at? Well, let's jump back in and see what's going on. You've got a y out in front. Understand, that's not one of our substitutions. We keep this y right here. Y double prime becomes p times dp dy. Y prime is just a p. And what you have now is a brand new differential equation Most importantly, you're going to notice that the highest order derivative is a first order. You no longer have a second derivative in the problem at all. And let's see, we've got yp is equal to dp dy equals p squared. You could divide both sides by p if you'd like. But ultimately, I hope what you're seeing is this is really separable. I hope you're seeing that. It's separable. Look, what you can do real quickly is divide both sides by p squared. And if you do that, now immediately kids might be like, why are you doing that? Also, I'm going to multiply both sides by dy in just a minute. See what's going on? This is completely separable. You've got 1 over p dp equals 1 over y dy. Wow. Hey, look at that. So guess what we're going to do now? Integrate. And let's see, the integral of 1 over p, natural log of p. Here you get the natural log of y plus a constant. By the way, you could call it C1. We can get to that in just a moment. Guess what we're going to do next? Well, you could. I would probably exponentiate first, right? Let's exponentiate. Okay? So this left-hand side, you could say, well, I've got the absolute value of p. The right-hand side, wow, we've been doing this so much, guys. You get the absolute value of y, but remember, e to the c is just another constant. You could call it c2 if you'd like. And dare I say, solving for p, it's either plus or minus with all of these. You honestly could just say that the plus or minuses are absorbed into the constant. If you have the absolute values in that regard, you've got a plus-minus issue. But constants could be positive or negative. So things are looking just fine. The thing is, p is actually what? dy dx. Okay. So now what? Well, we're almost done. Another separable differential equation. Take a look at that. Integrate. And we'd say this becomes the natural log of the absolute value of y. This becomes c2x plus some new constant. All right, don't forget that for these problems, guys, you will expect to see two constants taking place. We are so close to wrapping up. Guess what we're going to do now? Exponentiate again. So much of this is really just the same work. So we'd say the absolute value of y would equal e to the c2x, but the plus c3 we could say is actually another constant. The y is technically going to be another plus minus when you solve here, but imagine that the plus minus just absorbs the constant. So it's a two-parameter family for a solution. It looks something like that. Okay, you guys doing all right? Okay, so two different cases that we could have. So we're going to do the worksheet.